Welcome back, ladies and gentlemen. Here today we're talking about this idea called Hooke's Law. And it obviously is going to deal with springs, but I want to mention that it's not so much a law as it is a very good approximation for many situations involving springs and how springs work and how they respond to different situations. And so I got some examples here. This spring looks like the coils are all, when it's at rest, they're all touching each other. If I bend it, you can see them spread apart. I can pull it, and you can see I can stretch that spring, and it wants to spring back. It wants to pull back, right? Rubber band obviously kind of does the same kind of thing, where if I stretch it, it kind of wants to return, and the whole snapping the rubber band thing. You're accustomed to that. Rubber bands are kind of interesting, even though they do have a force that they pull back with. Rubber bands typically don't obey Hooke's law. It's very strange. And even a regular spring like this, while under some conditions it will obey Hooke's law, you could do stuff to any spring that would cause it to sort of, I don't know, not violate Hooke's law, but would not be what's what I'm looking for. Would not be demonstrating Hooke's law. Would not be well modeled by Hooke's law. Here you see a spring inside of this little scale. It's a spring scale, and the harder you pull, you hang a mass on here, and the spring responds by supporting it at a certain level. And if you hang more mass that has larger weight, it comes out here, and the spring has to pull harder back to keep it there. And so a spring scale is the same kind of principle. This thing, paperclip, obviously, and what makes this a spring? How does it hold papers together? Papers are put in between, and it kind of clamps down. Now, with all springs, all materials, you can bend them more or less, but you know what happens to a paperclip if you bend it too far, right? It doesn't go back all the way. And even further, and then oops, and if you're doing this to a spring, then it's not obeying Hooke's law anymore, and you're doing what's called plastic deformation. It's permanent deformation in the material. Can you do that to a rubber band? Actually, you can. You can stretch these too far, and they'll break. I don't want to do that right now, but I can show you another example. A spring like this one. Check this out. Originally, the coils of this spring were nice and compact, and it could be stretched, and it will pull back to its original shape. You know what's happened here. This segment has been stretched too far. Now, what's interesting about this is you can see clearly that not only can a spring stretch and return, but a spring can be compressed, and it wants to return. So this is useful in demonstrating that, at least. But you can damage springs by pulling or pushing on them too hard. It is possible. Okay, but let's get to this. What do springs really do? Right? Let's look at a situation. I'm going to have a setup where I have some object. Doesn't matter what it is, and it's attached to this fixed surface by a spring. And so at rest, currently there's, let's define sort of no stretch or compression on the spring. Okay, well, what does that mean? Well, that means that the spring is just in its neutral position. It doesn't want to do anything to you, or doesn't want to do anything to this object. Let's label a few things though. I've got this location here, and this is a distance of L. Let's call this the resting length. L will be the resting length of the spring. No stretch or compression. Let's call this position, just for a reference, the zero position, and let's make positive to the right. Just so we have some coordinate system that we can work with, because it actually will matter here. Now, imagine that the same object, same situation, same spring, is stretched, is pulled to the right some distance. Okay, so the spring is stretched a little bit. What was the resting length? The resting length was here. And so here's the origin. Positive is still to the right. But this displacement right here, from there to there, let's call that displacement x. And it was a positive displacement. Okay. And we still have L right here, right? Still have resting length L. Okay, well, what's going on? What's the spring going to want to do in that instance? We've taken this and we've pulled it to the right. The spring wants to pull back. Yeah? So there is a force exerted by the spring. I'm going to move my label down here. There's a force in the x direction caused by the spring wanting to return. So we've stretched it. There we go. Stretched X amount. And we see the spring want to return with force F in the X direction. Okay. And so that's all well and good. But what if we've stretched that object, pulled that object even further to the right? Let's see where this is going. I'm going to actually pull it twice as far. So roughly here. Okay. Same spring, pulling it further. I don't want to pull too far. I don't want to damage the spring. I don't want to exhibit plastic deformation. That'll kind of ruin the spring. Remember, the resting length was here. So there's the origin. Positive still to the right. How far did I stretch it? I stretched it a distance of 2x, this displacement. Twice as far. Okay, here's L, resting length. And so what is a spring going to do? What we find with most springs, well, maybe I should just say many, and that's really the only kind of spring we're going to concern ourselves with, are springs that do obey Hooke's law. Many springs do obey, some don't. The spring responds with a force twice as large. It responds with 2 times the force in the x direction. Okay, so let's make note of that. Stretch 2 times further, or a distance of 2x. And the spring wants to restore or return with a force of 2 times F in the x direction. And that's testable, that's measurable, it's been demonstrated many times. And in fact, that's what happens with your spring scale. You stretch it to show a mass of 100 grams, okay, then to stretch that spring twice as far from its resting length, you have to get it to 200, and it's trying to pull back with twice the force. Well, it's supporting twice the mass, which would be twice the weight. It makes sense. Springs are very useful things. Now, what does this mean? So is there some relationship, some mathematical relationship we can do, sort of come up with for Hooke's law? Let me get all my stuff out of the way here, and let's check that out. So, Hooke's law. Not really a law, more of a rule of thumb or guideline, but springs, it's a very good guideline for springs in many useful situations. The force that a spring exerts in some direction, remember, this is the force that the spring exerts. When I'm doing this, I'd have to pull on this object this way. I'm not talking about the force I'm applying. I'm talking about the force the spring is exerting. Oh, and we'll come back to that. But we find that, well, it's definitely sort of a linear relationship with the displacement from the resting length, and there seems to be this constant that's found, and you could test for a certain displacement the force and do that over and over for various stretches of a single spring. But then you test a different spring, and you find that for the same amount of stretch, it requires a different amount of force. And so different springs have a different value of this guy. Now watch this also. We'll come back to that K in a second. Notice how our displacements were in the positive direction, and our force, the spring force, the restoring force, was in the negative direction. The direction of that displacement and the direction of that force will always be in opposite directions. So we need a minus sign here. This is Hooke's law. Pretty simple. But how about this spring constant? That's what this is called. Sometimes you'll hear the word force constant, but spring constant. Okay. So first of all, it has units, because if I isolate this and I divide force by displacement, I'm going to get units of newtons per meter. So spring constant has units of newtons per meter. And that's the traditional way of looking at this. Larger values of K indicate a stiffer spring. I'll show you some in a second. So, what does that mean? Well, if I show you a spring that is this size, and then I show you a spring that is, oh, it rolled away, this size. Okay, I'm on my A game today. Oh. If I have displaced the small one by 1 centimeter, then maybe I should do it this way so I'll be consistent with my direction. I'll displace 1 centimeter. That requires a certain amount of force for this spring. A displacement of 1 centimeter on this guy requires a different amount of force. I can feel it. And I could also measure it if I had the instruments set up. And so these two springs would have different spring constants. One would be stiffer, one would be more pliable, more compliant, however you want to say it. And so what else is going on here? Well, remember that the spring force is in the opposite direction of that displacement, and it always will be the case. You want to think of this force as a restoring force. Let me write that down. That's going to come up again later. A spring force is a restoring force. Remember that. Well, okay, let's look at a quick example, and then we'll wrap this one up, right? I'm going to want more space for my example here. Okay. We're going to look at a situation that's with the spring is arranged vertically this time. Okay, there's our spring. And it's sitting here at its resting length. An ideal spring. The ideal spring itself typically doesn't have any mass, and there's no internal friction, which is, in real life, for very, very delicate or sensitive situations, the friction and internal resistance and weird things are going to affect things. But, pardon me, on a scale that we're dealing with, not going to be an issue. On to this spring. We're going to place an object. Doesn't really matter what it is, but the object will compress the spring. And we can look at the amount of compression, right, from there to there. And what other information will we have? Let's say we have a direction that's positive, as up. That's sort of traditional. What about this object? What do we know about it? Well, let's say we know the mass. 9.09 kilograms is the mass of that object. And what is this displacement? What from resting length? So instead of x, I'll use y. And it's in the downward direction, so it's going to be, so up is positive. This will be a negative displacement of 4.18 centimeters. Okay. right away I might recognize that I'm going to convert that to meters. And my job is find the spring constant by the value of K. All right. I know the mass. No, what I don't know right away anyway is the restoring force. Let me see if I can figure that out. So this has, this object has some forces acting on it. And one of the forces acting on it is that restoring force. Which way should I draw that restoring force? The restoring force is opposite of the displacement. The restoring force is upward, right? There's F in the y direction caused by the spring. Are there any other forces acting on that object? There certainly are. There is weight. This object has mass, it's got weight. I'm going to dot for the center of it, and so there's not weight downward. Oh my goodness, okay. And so what do I do with this? Of course, I make a free body diagram. Nothing happened in the x direction, so that's boring. And y direction, here we go. It's something that's observed. This thing, when it's placed upon the spring, the whole system reaches a new equilibrium, a new stable state, and that means no acceleration. So with no acceleration, I don't necessarily know how long to draw this arrow, the force in the y direction caused by the spring. But what I do know is that these two arrows should be equal length. Okay. And why is that? Well, I can verify that, or not verify, but I can sort of justify that, reason that, because I observe no acceleration. The sum of forces in the y direction is equivalent to a mass times acceleration in the y direction. I observe no acceleration, therefore this is 0. But what are those forces? Those forces are the spring force in the y direction and the weight in the downward y direction, the negative y direction, and that is 0. So this guy equals that weight. Oh, but I know what weight is. It's mg. And so I can find this spring force, this restoring force. The mass is 9.09 kilograms times g, 9.8 meters per second squared. Okay, so what is this spring force in the y direction? Rounded numbers, it's 89 newtons. All right. Well, cool, but that's not the answer I need. I need to find K, the spring constant. Now, though, I know the spring force, so and I know the displacement. So let me pick a color that's pretty good. That might be too light. You know what? That'll work, actually. I believe that'll work. Watch this. Here's Hooke's law. Force in the y direction equals negative K y. Remember, it's not x, it's just y up and down direction. Isolate this, solve for K. I get negative force in the y direction divided by my displacement in the y direction. Okay, and I know those two numbers now. So, negative force in the y direction is a positive force, and that is 89 newtons. And I'm dividing by the displacement, but the displacement is now negative. And it's 4.18 centimeters. I'm going to convert that to meters. 418 meters. So I'm dividing by, clarify my fraction there for you. And I work out a value for K. It's going to be kind of large, 2,130 newtons per meter. There it is. That's the spring constant in this case. And notice what I had to do. I had to understand the situation, the force is acting on this object, and one of those forces is the restoring force of the spring. It helped to do the free body diagram, even though I wasn't explicitly asked for it. Once I do this, I'm almost 100% of the time certain I'm going to want to do this, which is a Newton's second law kind of statement. And that tells me something. I can figure out this force of the spring. And then I work through this to get the spring constant. Brilliant. So essentially it's pretty simple, right? Hooke's law, and even a rubber band under a certain amount of its stretch might obey Hooke's law, but a lot of springs do. And that's about what you have to know. We will apply Hooke's law in various situations, and the situations will become more complicated, but Hooke's law itself is just that simple. Thanks for watching. I'll catch you next time.